Hello, this is the second part of the chapter 3.2, and we'll talk about determinants of reduced echelon form of the matrices or echelon form of the matrices. We don't always have to reduce it, row reduce it. Okay, but let's start by thinking about the square matrix and when it has invertible. We started whole this determinant business to actually figure out as soon as possible if our matrix is invertible or not. We know that being invertible is really important. We can do a lot of things if our matrix is invertible. If not, we have to give up. And the faster we recognize if our matrix is invertible or not, the better it is for us. So determinant or if determinant is zero is really important. And our echelon form for square matrices is very useful because it can tell us if determinant exists or even to calculate the determinant. For example, if our echelon form matrix, for example, here matrix U has pivot element in every single column, then we are lucky because our pivot elements are non-zero. When we are multiply them, that gives us a determinant which is not equal zero. And determinant not equal zero, according to theorem 4, means that our invertible matrix exists. So what if we are not as lucky? What if our echelon form matrix missing pivot element in some of the columns? That's not very good because it's still triangular matrix. We can multiply the diagonal element, but because some of them equal zero, it's inevitably give us determinant equal zero. Or according to theorem 4, we will know that our invertible matrix in this case does not exist. And this gave us a really good tool for fast finding existence of the invertible matrix. And we can even summarize it a little bit more formally. For example, let's assume that we have a square matrix A and we reduce it to the echelon form by just by usual row replacement and row interchanges. And because we know the row interchange, we have to change the sign of determinant. Let's keep in track of them and let's count how many of them. And let's count the number of these interchanges called it R. Then we can write down the formula for our determinant, which consists of these two major cases. And again, as usual, this curly bracket over there tell us that there is two major cases in our definition. So we can have a case number A when matrix is invertible. In this case, our determinant will be the product of pivot elements. This is our left case here. It will be just the product of pivot elements in our matrix U times -1 in the power of number of interchanges. So basically, if number of our interchanges is even, sign would be positive. If our number of interchanges is odd, the sign will be negative. In other case, if our matrix is not invertible, that is, we're missing at least one pivot element in our echelon matrix. In this case, the invertible does not exist and our determinant will be equal zero. Okay, let's see how this information can help us to determine is invertible exist or not, or compute the determinant really fast. For example, let's see matrix A here, rather large matrix. Let's see if we can calculate the determinant for this matrix. And again, we're starting by writing down our matrix, and our first step is always, try to reduce it to echelon form. And the second row here, we have a 0 element in the first column. This is nice. So we as usually tackle the next element, which is the third row, first column. And instead of -6, we would like to have 0. So we double the first row over there and add it to the third one. And indeed, we have a really nice 0. And probably your desire, the next step you want to conduct is just tackle with this -5 element to complete the row, the column of zeros. But I urge you to stop and look at our second and third row. They are identical. And that means that at some point when we subtract one from another, we will have a whole row of 0. And that's not the good news, because if we have a row full of 0, it means that at least one of the pivot column is missing. So we are definitely going to this right scenario. So our invertible does not exist, and we will have at least 1 0 in diagonal element. So our determinant is equal 0. We don't need to carry out any calculations. That simple observation is suffice. Okay, and that's how we can find determinant really fast if we follow in the property of the matrix. Okay, and now I would like you to go back to the end of the chapter 3.2 and calculate, reduce several echelon matrices and calculate their determinants.